Welcome to The Explainer. Today, we're going to break down the huge engineering and safety challenges behind one of our most talked about climate technologies, carbon capture and storage.
You know, the scale of this problem is, well, it's just staggering. To even have a chance at hitting our climate targets, we have to build a brand new carbon capture industry. And get this, in just a couple of decades, it needs to be bigger by volume than the entire global oil industry that took over a century to build.
Because here's the thing, it turns out carbon dioxide isn't just some harmless gas you breathe out. No, when you compress it and try to move it in these massive quantities, it becomes a surprisingly difficult and, hazardous substance to manage. All right, let's really dive into this.
Okay, first up, let's just get a handle on the whole process. Engineers call it the CCUS chain, and it's basically a journey with some pretty critical steps.
So it's this four-step trip, right? From the smokestack all the way to being locked away in stone. But here's the catch. Each and every one of those steps presents its own unique set of engineering puzzles. And the real heart of the problem, it lies with the tricky physical properties of CO2 itself.
To really get why this is so risky, we have to get into the weeds a bit, into the weird and kind of volatile properties of highly compressed carbon dioxide. It just doesn't behave like other industrial gases we're used to.
So, in simple terms, what's the Joule-Thomson effect? Well, when you let a compressed gas expand really fast, it gets cold. Just think about that cold spray that comes out of an aerosol can. Yep, that's it in action.
But here's where CO2 is a total outlier. I mean, just look at these numbers. Its cooling effect is 3, maybe even 4 times more powerful than other common gases like nitrogen or methane. So a pressure drop doesn't just cool it down a little bit, it causes an extreme and incredibly fast deep freeze.
And that massive cooling factor, it creates 2 absolutely critical safety risks. First, that intense cold can make the steel in a pipeline as brittle as a piece of glass. And second, it can literally form solid dry ice that can clog up the very safety vents that are designed to prevent a disaster in the first place. And on top of that, you've got a chemistry problem. If even a tiny amount of water gets into the CO2 stream, it forms carbonic acid. Now, it's a weak acid, sure, but it's more than strong enough to start corroding standard steel pipelines. That means the CO2 has to be kept unbelievably dry. We're talking below 50 parts per million of water, just to stop the infrastructure from basically eating itself from the inside out.
So, just to recap, we have a substance that can make steel pipes shatter from the cold and corrode them from the inside. Now, imagine trying to move millions of tons of that stuff across the country. This is where things get really hazardous.
And this is exactly why safety experts are so clear on this point. Even though CO2 is, all around us in the air, at the pressures and volumes we need for carbon capture, you absolutely have to handle it with the same level of caution as any other dangerous industrial chemical, period.
One of the biggest fears for pipeline engineers is this thing called a running ductile fracture. And let me tell you, it is exactly as terrifying as it sounds. If a tiny crack forms, the escaping CO2 creates this decompression wave that shoots down the pipe, and the crack can actually propagate along that wave, literally unzipping the pipeline for miles at nearly the speed of sound.
So to manage these huge risks, engineers use different strategies depending on where they are. Onshore, especially near places where people live, they often go for lower pressure gas transport. It's less efficient, but a leak would release a lot less material. Offshore, though, they use a high pressure dense phase where the CO2 is almost a liquid. This can carry 400 times the volume in smaller pipes, but the risks are way higher. It's this constant balancing act between efficiency and public safety.
And, even when the CO2 gets to the end of the line, to the storage facilities, the dangers don't just magically disappear. In fact, in some ways, they actually pile up.
Have you ever heard of a BLEVE? It stands for Boiling Liquid Expanding Vapor Explosion, and it is an absolute worst-case scenario for any kind of pressurized liquid storage. It's this incredibly violent explosion caused by the whole tank's contents flashing into vapor almost instantly. For a long time, people actually debated whether this could even happen with CO2. Well, that debate is over. We now know it's definitely possible. And the really worrying part is that the conditions you need for BLEVE, storing the liquid above about 18 degrees Celsius and 56 times atmospheric pressure, are precisely the conditions that are often used in the industry for transport and storage. So a catastrophic tank failure could be, well, truly explosive.
So with all these insane risks, how in the world do engineers actually tame this beast? Well, they use a really sophisticated toolkit of design, analysis, and of course operational procedures to manage all these hazards.
Look, this isn't just guesswork. It's a systematic, multi-layered approach. It all starts with rigorously modeling every possible way things could go wrong. It involves carefully picking specialized materials that can handle the extreme cold and the corrosion. It means using advanced tech like fiber optic cables buried right alongside the pipelines to detect the tiniest leaks. And it all gets tied together under comprehensive international standards that basically write down all the best practices we've learned from decades of industrial experience.
So the takeaway here is pretty clear. Safely managing carbon capture and storage is one of the great engineering challenges of our time. It means we have to master a volatile and hazardous material at a scale we have just never seen before. The technology and the know-how, they exist. But deploying it safely all over the world, that's going to take immense diligence, a lot of investment, and an absolutely unwavering focus on safety.